In this video, we'll be discussing topics from week 7 of Physics 259, which talk about current, resistor, and capacitor circuits. We also talk about resistance, resistivity, conductivity, as well as Ohm's laws and some equations that we can use for this section. So the first thing I'd like to talk about is conventional current. So usually we think of current as the motion of electrons, but conventional current is the flow of positive charges through a circuit. So you can imagine, I guess, this positive hole displacing an electron, right? And as that electron moves this way, positive charge is going to flow the other way. So I'm going to use the green arrow to show the flow of the positive hole, right? And you can watch as it travels to the next spot as each electron displaces it. So this is thought of as the flow of the positive holes within a circuit. So it flows from positive to negative, and our electron flow flows opposite of conventional current. Okay, so this is just a way to visualize what conventional current means when we talk about it. And now we're going to talk about electrical current. So it is the time derivative of charge passing through a cross-section of a plane. So in your diagrams, you're going to see these little dots with arrows on them, and this dictates the movement of the current, right? And this is called an amp. So it's a coulomb per second, which makes sense because in this equation, our current is equal to the derivative of charge over the derivative of time. So it would make sense that our unit is coulombs per second. All right, and if you were to do it over a specific time interval through an area, you can use integration to show charge. So we're taking this equation and rearranging it, where our bounds are time and our current is inside the integral. So Kirchhoff's current law states that all current entering a junction is equal to current exiting a junction. So if we have a circuit that looks like this, where our electron flow looks like this, sorry, our current flow looks like that, and we want to write an equation for this junction here where they all intersect. Let's say this is I1, I2, I3. So I1 is entering, and I2 and I3 are leaving. So you could say that I1 minus I2 minus I3 is equal to 0, right? So yeah, if you rearrange, so I'm going to say current flow should be equal to 0. So this relates to our current law, and we can use this hand in hand with our knowledge of Kirchhoff's voltage law, which states that in a closed loop, our voltage through each one adds up to 0. So using this knowledge, let's work through this example. So example 1 gives us a current and determine the amount of charge that flows through a cross-section in the first 10 seconds. So seeing charge and seeing this should indicate to you that you are going to be using the the integral function for this t2 at the top bound t1, and you have I dt. Okay, so we're going to find charge from in the first 10 seconds, so this is from 0 to 10 seconds in our time, and our I is equal to I naught, which is 15 amps. That's 15, that's e to the negative t over 2. Okay, and this is dt. Then Q is going to be equal to, so kicking out this 15, which is a constant, and integrating this gives us negative 2e to the power of negative t over 2, and from our bounds 0 to 10. So then this gives us 15 negative 2 e to the negative 10 over 2 minus 15 e negative 2 and e to 0 over 2. And this is equal to, this becomes negative 30 and e to the 5. And this is plus 30. Because this becomes 0, that turns this e into 1. So this becomes our charge. And if we plug this into our calculator, Q becomes 29.8 coulombs. Okay, so now we're going to talk about current density. So like charge density, current density is going to be represented by a J, and this is equal to amps per meters squared. Okay, so that it's the amount of current that is flowing through a certain amount of area. And in this, our J is equal to, so our current density is equal to our time derivative of current. So in that similar vein, we can say that our current is equal to the dot product of our J times our dA, which is equal to the integral of J times dA as just a magnitudes times cos theta. So we're going to use this equation in this next example, where we have a cylindrical wire with radius r oriented in the x-axis, where the current density that increases with radial distance is J equals kr in the I direction. So in the positive I direction, that means it flows like this. And we want to derive an equation for the total current passing through the cross-sectional wire. So we know our equation for current is I, and that's the derivative. And we want to integrate from R to R0 because we want to consider this as infinitesimally small rings. Right, so we want to integrate with each ring, where our furthest is R, and then our least is just 0 at the center. And this was our current density, the dot product of our area. So since J is constant, sorry, what I meant is since J is parallel with dA, right? Because if we want to have our cross section, we can imagine our dA pointing outwards like this. Then that just turns this into, so since our cos is 0, that just gets rid of this dot product, and it's just our J times dA. And plugging in for our values, J was given by K times R. And this is multiplied by the derivative of our area. So if our area is equal to pi r squared, We take the derivative of that and move that 2 down. Right, we end up with this value. So we're going to plug that in. So 2 pi r dr. Right, and we're going to take out our constant. So k was some scalar constant. We're going to take out k and this 2 pi, and we're going to integrate with respect to r. So then this becomes 0 to r. I'm going to kick out the k 2 pi, and this is r squared dr. And when we integrate this, this is going to be 1 over 3 r cubed. And this is from 0 to r, it's going to be 1 over 3, then this is r cubed. Okay, and that is the equation for this question here. So next we'll talk about drift velocity. So drift velocity is the average speed of electrons in current movement. So drift velocity can be derived from these equations here, where n is the number of conduction electrons per unit volume. So these are electrons that are free to move that we can actually use in our calculations. And the number of conduction electrons in a length of wire is n times v equals NaL. And the amount of charge in a length of wire is thus Q is equal to our elementary charge times the number of electrons we have, times area times length. This is just our volume, represents our volume of our wire in this case. The magnitude of drift velocity is equal to our length over time, right? So this is kind of like velocity equals distance over time, right? Where distance is now replaced with our length and time stays the same. So since since current is charge over our time, we take our equation for our charge here, and then we put it over our drift velocity, our time, right, which was from our drift velocity equation. We find our lengths cancel out, and we get this equation here. And now when we take this equation and we find for our current density, we can plug our current over our area and get this equation here. Okay, up next we're going to talk about resistance and Ohm's law. So resistance is probably a term you've heard, which is a property an object has to resist flow. Oops, sorry, hold on. So it's a property an object has reduce electron flow or current flow in a circuit. And you may have used these in some practical applications like LED lights. When you wire an LED light, it's important to have a resistor, or else you could end up burning out the light by overloading it with the current flow. So that's what resistors do. And Ohm's law is a way to relate current, voltage, and resistance, where V equals IR. Resistance is in ohms, right? And now let's talk about resistivity and conductivity. So resistivity is the capacity or ability for a material to resist flow and it is specific to temperature in Kelvin, and it is specific to the material that is being used. So usually on an exam, they will give you these values, so you can find those properties for yourself. You're not expected to know or memorize them. So usually you'll be given those quantities on your own. Resistivity is modeled by this equation, which is rho is equal to our electric field over our current density. And we have a specific way to find what our rho can be. So this is going to be represented by this equation. So then that's times alpha, and this is our change in temperature. Okay, so this is our temperature dependence equation. And we are given our values for our rho naught, our temperature dependence, and our change in temperature. Okay, and conductivity is going to be the inverse of our resistivity. So this is equal to 1 over rho. Right, and like the name suggests, conductivity is the capacity for an object to allow electron flow rather than resist, like our resistivity. Okay, so let's use this knowledge in an example. Using our equation above, we can find what our value for our resistivity. So rho is equal to rho naught times alpha, and this is our given temperature minus our T naught, which we can find from a tabulated value, and this is plus rho naught. So this will equal, so it's 2.35 times 10 to the negative 8, and this is times alpha, so that's 4 times 10 to the negative 3, and this is our change in temperature, which is, so we're starting at 300, which was given in our question, minus 293 Kelvin, and this is plus 2.35 times 10 to the negative 8. Okay, and this is equal to about 2.42 times 10 to the negative 8. This is ohm meters. Okay, and we're going to plug it into this equation here. So we're looking for resistance, which is equal to, so if we look at our V equals IR equation from Ohm's law, you can see that R would be equal to V over I. So in this case, we're going to use this equation, our resistivity times our length over our area. Okay, so this is just a different model or representation of our previous equation. This will be 2.42 times 10 to the negative 8 ohm meters, and this is divided by, so our area squared, so our area of our cross section, sorry, not squared, just regular area, so this is 1 centimeter in length, and we have 0.5 centimeters in radius. So we know our area is pi r squared. And this is multiplied by our 0.01 meters. Right, and you're going to see that our meter squared cancels out with this meter and this meter at the top, so it's only going to leave us with a value of ohms. That means that our analysis is correct. So this is 2.42 times 10 to the negative 8 times 0.01 divided by pi times 0.005 squared. And this is 3.081 times 10 to the negative 6 ohms of resistivity. Okay, so now moving on, this is a molecular view of Ohm's law. So we know that from Newton's second law that F is equal to ma, and we know that electric static force is equal to Q times E. So if we plug that in for our value of F here, then we can isolate for what our acceleration is, which is going to be Q times our electric field, which equals, over our mass. And that's going to equal this, where E is now our elementary charge because we are working with electrons. So as electrons travel, they collide with other atoms and other electrons along the way, which slow down and change their direction. And this is what resistance is. Resistance is the result of these collisions. Right, so by putting something in the way of the travel of our electrons, it slows down their movement because it makes their directions more random. And this is what drift velocity was. We could also express drift velocity as acceleration times tau. Right, so we previously expressed drift velocity as our length of our wire over time. So this is just a different version of that, where our acceleration, which we got from over here, let's use a highlighter, is now being used here in this equation, multiplied by tau. So that makes so plugging in for drift velocity here, we can find what our charge density is. And in our electric field, we know electric field is our resistivity times our current density. And we can plug for our value in there to get rho is equal to mass over our number of electrons times our elementary charge squared over tau. So just a different rearrangement of equations based on this property up here. Okay, so we're going to talk about RC circuits. So RC circuits are, so resistor, and capacitors connected together in series. So RC circuit could look something like this, where you have your voltage source, you have your resistor, your capacitor in a circuit together. So there's really specific properties that are going on here that we can talk about. So when we look at some equations here, we define our charge using this equation, and we define our time constant with this equation here, which was derived from our Ohm's law. Right, and this shows how we derived that to only get a unit for seconds. This is our capacitive time constant. So this equation can also be written in this form. You can see something like this in the next couple units down the line when we talk about inductors, where Q naught is the initial charge on the capacitor, and T is the time that it takes to discharge. So this function, not sure if it's on here. Right, this function looks like this. Right, so it gradually plateaus, so it kind of curves along, and then the slope flattens out. So that just represents how our charge behaves in a capacitor as it is discharged. So we know that with our capacitor, we can turn on a circuit to charge it, and once we turn it off, then that charge is slowly discharged. It doesn't suddenly just cut off, right? So if you were to draw that without a capacitor, and you turned off the circuit, so this is your current, and you turned it off, it would look like that when you disconnected it. But if you had a capacitor attached, it would gradually decline and then flatten out. Okay, so that is why we have this equation to account for that property. So that means I, as a function of time, our current as a function of time is equal to our current naught times e to the power of negative t over RC. Okay. So there's also this equation here. This is the potential difference across a capacitor. And this kind of is the same thing. So you can use for each equation for our charge, current, and voltage, right? Each of them looks like that specific variable naught times e to the power of negative t over RC. Okay, so we're going to put this to use in this example. In this example, we are given a RC circuit that is connected in series with a capacitor and a resistor, so this is RC circuit for sure, with a 22-volt battery. So after 80 nanoseconds have passed, it is asking us what the current is. So current as a function of time is given as I naught, it's e to the negative t over RC. Okay, so we don't have our I naught, so how would we find it? Well, that's simple. We're going to use our V equals IR equation. We're going to isolate for R, so this is V over R in this case, and this is 22 volts over our resistance value of 50. So this is equal to, actually, you know what, we're going to just keep it in this fraction. So that is what's going to be going into our equation. Let's solve for this exponent on its own. So solve exponent on own. This just makes it easier to plug back in. So this is given as negative t over RC. This is equal to, so negative 800 nanoseconds. It's 10 to the negative 9 seconds. This is over 50 ohms. And our capacitor is 87 times 10 to the negative 9 for nanofarads. And this is going to be negative. So it's 800 divided by 50 times 87, because these are going to cancel out, and this becomes negative 0.1839. So we're going to plug this back into our equation. So this is, our current is equal to, so we're going to use what we found in our green for our initial current. This is times e to the negative 0.1839, and this is equal to, so 22 divided by 50 times, and then this will give us 0.366 amps for our current. Okay, so note that this equation only applies to these specific RC circuits. Okay, so we have a 30 nanofarad capacitor, and it's discharged through a 10 ohm resistor. Okay, so at t equals 0 seconds, the potential difference across the capacitor plates is 5 volts. And at what time is the potential difference 50% of its initial value? So this initially equal to 5 volts, then we want when our voltage is equal to 2.5 volts. So we want to find at what time we will get that to happen. So what we can do is we can rearrange for this equation. So we're going to use this equation right here to help us find what our new voltage will be, our new time will be. So this is V equals V naught times e to the negative t over RC. Okay, and when we take this V over V naught, this is essentially what's equal to our, hold on, sorry, this is our new value. So this is like saying 5. I'm so sorry, I'm all over the place. Okay, bring it down over here. So this is essentially saying 0.5 is equal to this. Okay, so let's apply ln so we can find what our value for t is. Sorry, this is ln of 0.5, so we add ln to both sides. And this is equal to ln of e to the negative t RC. This exponent is going to come down. Ln times e is just equal to 1. So this is equal to ln 0.5. This is negative 0.693147. Okay, and we know our value for R and C. So let's get rid of that negative on either side. And T is equal to 0.693147 times our RC. So I'm going to just put our value. So we have 10 ohms for resistance, and we have 30 times 10 to the negative 9 farads. And this is equal to 2.0, and then times 10 to the negative 7 seconds. Okay, so that brings us to the end of the notes section of this video. When we come back, we're going to work through some Wiley Plus examples that relate to these questions that talk about resistors, Ohm's law, resistivity, conductivity, and RC circuits. So we'll talk about that a little bit more when we come back. I'll see you then, and thanks for watching.